This video is going to look at the Diels-Alder reaction and the analysis of the data from that. To start, this slide does show the aldol as well, but you don't need to discuss that. Do note that there are two reactions that you need to mention in your abstract and show in your chemical equations. First is the reaction to synthesize the benzyne from anthranilic acid and isopenyl nitrite. And then the second reaction, of course, is the Diels-Alder itself, the reaction of the tetraphenyl cyclopentadienone with the benzyne to form the tetraphenyl naphthalene. The guidelines for the report are same as always. Don't forget to include moles or millimoles for your reactants and catalysts, but not for solvents. Also, since you are obtaining a melting point, you do need to report that along with the literature value. And then, of course, you always report spectral data. For IR, you've seen this before, the units, frequencies, and we list those one at a time. UV, the ultraviolet visible spectrum, similar, we report the medium or the solvent, in this case hexane. Since we're not reporting an actual frequency but a proxy, we designate what that proxy is, and in this case we're measuring wavelength, and so we give the symbol for that, and the conventional symbol for wavelength is the Greek symbol lambda. This is the lowercase lambda, so you can make a lowercase l and convert that to a symbol or Greek font to get the lambda. And units are nanometers, and again you simply list the individual frequencies. Do note that regardless of how broad a peak is, you give a single value at the lambda max for that peak. For carbon-13 NMR, again we do solvent units. Again, we're not measuring an actual frequency. Part per million is a surrogate or a proxy for frequencies. And so again, we designate that by having the delta there to designate it. For proton, we reported the chemical shifts as well as coupling and integration. In this case, everything is decoupled, so there is no splitting, so we don't need to show that, and the integration is messed up by the decoupling, and so all we report are the frequencies or the chemical shifts one at a time. Calculations, limiting reactant theoretical yield, percent yield. Do remember you have 3 reactants, so you need to do limiting reactant calculations for all of those. And also remember the isopenyl nitrite was used as a solution. And for solutions, you use the equation molarity times volume is equal moles to calculate the number of moles. Do not treat it as though it is a pure liquid and use density and volume. We use molarity and volume for. So the analysis, IR, you've seen this before. This is for the aldol product. You will be doing it for your product. Again, if you have multiple peaks, give a range. Do note, for example, that here we actually have multiple peaks, so we give a range. The fact that only one of them has a frequency attached to it does not mean the other peaks aren't there. And don't forget, when you're looking at aromatic compounds, in this region around 1700 to 1800, you'll often have little peaks, looks like little waves. These are the aromatic overtones. So make sure you look for those and include them. And one other comment about IR. It is important to note peaks, relevant peaks that are not present, or bond types that are not present. For example, for the aldol, one of the reactants was dibenzyl ketone. It had this structure. Note that we have 2 methylene groups, the CH2s, both of which have sp3CH. The fact that we don't have any peaks between about 2800 and 3000 indicates that we do not have sp3 hybridized CH, and therefore we don't have any of the starting material. You should make note of the same thing with your product. The absence of a peak or peaks, there's one in particular, I'll leave that to you to figure out, but there's one in particular that is present, in two of the starting materials, but not in our product. And you should simply make note that that peak is absent, indicating that we do not have starting material. We do have a new material, we do have a new product. Now let's talk a bit about the NMR, the interpretation. The spectrum we see here, the way we approach this, start with the chemical shifts. Note out around 200, we do have a peak there. This is the region where we typically see carbonyl, and so we would enter that into our table. This tells us a small amount about our product. The rest of the peaks, and I'm going to zoom in on that region, but from about 155 out to about 125, all of these peaks are in the region where we would expect to see carbons for alkenes and aromatics. And so simply looking at chemical shift doesn't give us a whole lot of information. It does tell us we have a number of peaks in that region. It's important to mention those. But we would like to be able to get a bit more information for our interpretation, make the NMR a bit more useful. And to do that, we can look at some of the other characteristics. There is one that should jump out at you, something my daughter would have noticed when she was 8. So don't overthink it. She was not an NMR genius at age 8. That is peak height. You'll notice we have several fairly short peaks, a couple of intermediate height peaks, and then 4 tall peaks. So there are 2 factors that affect peak height. One you're familiar with from proton NMR, the number of nuclei. In proton NMR, the number of nuclei is directly, or number of hydrogens is directly proportional to the peak size. So if one peak is twice the size of another, we can conclude that it means there are twice as many carbons. This is a factor in carbon NMR, but there is a second factor to consider. But all else being equal, if one peak in the carbon NMR is twice the size of the other, then that peak will be represents twice as many carbons. And so we have that correlation here as well. But carbon NMR is complicated by a second factor, that's the nuclear Overhauser effect. Basically, carbons that have hydrogens have an enhancement. They will be quite a bit larger than carbons that do not have hydrogens attached. And so we can use this information to do a more in-depth analysis of the spectrum. Something to note here is that we do have some peaks, 4 of them in particular, that are roughly the same size but fairly short. So we've got one here, 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 and here. These peaks are all roughly the same size, relatively short. This indicates carbons that do not have hydrogens. So we could put that in our table. So we have a bit more information about our structure. We know that whatever our product is, it has 4 carbons that don't have hydrogens. The taller peaks then are carbons that do have hydrogens. In particular, we have these 2 right here. So these carbons have hydrogens, as do the very tall ones. We've got 4 of them here that also have hydrogens. But note that the intermediate, the 2 peaks, are roughly half the size of the other 4. Since both sets have hydrogens, that would indicate that the taller peaks, since the peaks are twice the size, represent twice as many carbons. And so we could add another row to our table, listing those 2 intermediate peaks, this one and this one, as representing carbons that are protonated, but are half as abundant as the other 4. I ran out of room on the slide, but there should be really one more row, and I will only partially fill that in, but we would list the peaks at 130, 129, and the other 2 right around 128 should be in that, and that would represent carbons, again, that are protonated, that are twice or 2x abundance, meaning there are twice as many of them. And so really there should be a 4th row, but again, I just ran out of room on this slide. Okay. And so we would put those in our table, And at this point, we can start trying to correlate it with what we expect is our structure. So we could draw our putative structure, and of course we label it, and then start making assignments and make sure that it matches the analysis that we've done. So at 200, we say that we have a carbonyl. We can check our structure, and indeed, we do have a peak with a carbon with a carbonyl, and that is the one that we've labeled carbon 1. The next step is to go to the next line. We've got 4 peaks which we have determined are carbons that have no hydrogens. And so we would look at the structure. Do we have 4 carbons that have no hydrogens? And indeed we do. Carbons 2, 3, 4, and 8 all have 0 hydrogens, and so those 4 carbons do fit as well. And so we could add those to the table as well. Carbons 2, 3, 4, and 8. We don't know specifically which peak is carbon 2 and which peak is carbon 3, but we don't need to make those specific ones. We do have more information at this point that our structure is, our putative structure is matching our data that we have so far. The type of carbon would be ideal if we have something a little more chemical, a little less carbons with no hydrogens, specifically those carbons on an aromatic ring that are in a point of attachment. So something other than hydrogen is bonded to it. We refer to those as ipso carbons, and so we can put that in as carbon type. Technically, carbons 2 and 3 are not ipso because the cyclopentadiene ring is not an aromatic ring. But we'll play a little loose with our description here and call those ipso as well, since they are the points of attachment. So moving on, we have labeled 2 carbons half abundance. So again, going from our data, we look at our structure, and we look, do we have 2 carbons that are protonated that are half as abundant as the others, the other protonated carbons? So if we look at carbon 5, we have 1, 2, 3, 4 carbon 5s. We have also 4 carbon 6. However, carbon 7, we have only 2. So we have half as many carbon 7s as we do 5 and 6. So carbon 7 does fit the description as a protonated carbon, and it is half as abundant as the other protonated carbons. So we can add that to our table. And then of course we are supposed to have, according to the data, supposed to have 2 such peaks. So we go back to the structure and look and see if there is a second one. And again, carbon's 9, we've got 4 of them. Carbon 10, we've got 4 of them. But carbon 11, we have just 2 of those. So carbon 11 is half as abundant as 8 and 9, or excuse me, 9 and 10, or 5 and 6. So that one also fits in here. And as I mentioned on the previous slide, we do have, or should have, one more row in this, which would list the other 4 peaks, the 130. And again, a lack of space, I didn't put those in, but the 130, the 129, and the others, and those would be carbons that are protonated of 2x abundance. And again, we have already marked those as being carbons 5, 6, 9, and 10. We have twice as many of those as we do carbons 7 and 11. And so the structure that we've drawn does fit the data that we have. Again, we would like to put the correct labels in for the type of carbon. And so 7 and 11 would be the paracarbons. The position opposite the point of attachment, or opposite the ipso, is the para position. And then position 9 would be the ortho, the one that's adjacent to the ipso position, and then the meta is the one that's one removed from that. So ortho would be a 1-2 substitution. The meta is a 1-3 and para is 1-4. But again, we should have one more row in that table. But this would be the ortho and meta, and again, we do not have enough information to distinguish ortho from meta, and so we simply link them together. This is the same analysis that you're going to need to do for your your Diels-Alder product. Approach it the same way. Start with chemical shift, look at the region, and state what region the peaks are in. Then break down the peaks in the aromatic region in the same way we did here. The shortest peaks are going to be carbons that have no hydrogens. Determine how many they are, and then you can correlate that with the peaks in the tetraphenyl-naphthalene, see if that corresponds. Then the taller peaks are going to be carbons that have hydrogens, and then we use peak height to determine the relative number. Again, if one peak is twice the size of another, it means there are twice as many carbons. And so you would do the same analysis that we just went through, doing that with the spectrum, and then seeing how it correlates with the structure. I will add one bit of information. Carbon NMR, because we're looking at a fairly broad range, 200 part per million, and all of the peaks are singlets, it is rare that we have overlapping peaks. Although you'll notice from this spectrum that we do indeed have two peaks that are not overlapping, but these two peaks are very, very close. Overlap is rare, but it can and does happen. The fact that I'm even mentioning it should be taken as a hint. To determine whether or not a peak is in fact overlap, you do need to use a bit of logic. And identifying such a peak, look at one that is unusually large. And then consider how many carbons does this represent. For example, in this case, we have the peaks at 127.5 and 128.5 represent 2 carbons. The other peaks are twice the size, so they represent 4. If we had a peak, for example, the two that are right there at 128.0, if those two were overlapping, we would have one peak, and it would represent 8 carbons, meaning it would be twice at the size of the others. So we could look at it and say, well, the peaks at 128.5 and 127.5 represent 2. The peaks at 129 and 130 are twice the size, therefore they represent 4. And then we would look at the one peak at 128 and recognize that is twice the size of the peaks at 130 and 129. If those are 4, that peak must represent 8. And then we would ask ourselves, what is the likelihood of a structure having 8 equivalent carbons? How much symmetry would that have to have, and is that likely? The more likely answer is that it is not in fact 8 equivalent carbons, but 2 sets of 4 that happen to be overlapping. They just happen to absorb at the same chemical shift, even though they are not equivalent carbons. And then you would simply enter it in the table, that one peak representing 2 different types or 2 different sets of carbons. When you're writing up your analysis, go through it the same way I just did, but you do have to justify. You can't simply say the peak at 140 represents carbon 1, the peak at 130 represents carbon 2. You have to explain why, give the justification. And you can do them in groups. You can say carbons or peaks at 140, 133, 139, whatever. These peaks represent these carbons, and give the explanation for that. All right. Moving on, you also have the UV visible spectra that you need to analyze. One of the spectra is given here, that for tetraphenylcyclopentadienone. Again, you will have a table, just as you do for NMR and for IR. One column will have the wavelengths, the other absorbance units, and this is really a dimensionless axis. Absorbance, we just put AU for absorbance units. They don't really mean anything. In fact, the absorbance depends on concentration, so if we increase or decrease the concentration, the absorbance goes up or down accordingly. But what we are looking at here is the relative conjugation. We're not interested in the other aspects that you can get from this. Sometimes you can correlate peaks with particular chromophores. For example, benzene rings typically show up around 255. So if you have a peak in that region, you can often associate that with one of the transitions in a benzene ring. We're not looking at that. All we're looking at is the relative conjugation between the tetraphenylcyclopentadienone, your starting material, and the product that you have, which may or may not be tetraphenylnaphthalene. So we will simply refer to it as the spectrum of the product. So in this one, we do have one extremely broad peak that has a lambda max here. When we're looking for relative conjugation, what we look for is the wavelength of the peak at longest wavelength. So we have a peak right around 500. That is the one at highest wavelength. We do have other peaks at 133 and 260, and one more at 206. But for conjugation, what we look at is the one at longest wavelength, and that is the peak at 502. So if we want to determine the relative conjugation of tetraphenylcyclopentadienone versus the product, we would simply look at the UV visible spectrum of the product. What is the wavelength of the peak, that one with the longest wavelength? We simply compare the two. Whichever one is absorbing at longest wavelength, that is the more conjugated molecule. So the UV visible spectrum is giving us information about the conjugation of TPC versus product. And we want to correlate that with TPC versus TPN. Which of those two molecules should be more conjugated? If the TPN is in fact more conjugated than TPC, and the UV visible spectrum says the product is more conjugated, then we may have TPN. On the other hand, if the UV visible spectrum says that TPC is more conjugated than our product, but tetraphenylnaphthalene is more conjugated than TPC, that would mean we do not have TPN as our product. So this isn't really going to confirm, yes, we definitely have TPN, but it will tell us that it might be or it definitely is not. So that raises the question then, how do we know which is actually more conjugated? And this is where Gaussian comes in. And we'll have to look at structures using the Gaussian program. And that one will tell us which is actually more conjugated. So the UV tells us TPC versus product, and Gaussian gives us information of TPC versus TPN. If they agree, if the Gaussian says TPC is more conjugated and the UV says TPC is more conjugated, then our product could be TPN. If they disagree, if the Gaussian says TPN is more conjugated and UV says TPC is the more conjugated, then we do not have TPN as our product. And so that is how we're using this. It should be fairly simple, fairly short discussion. Simply compare the wavelengths of the TPC and the product for the longest wavelength peaks and determine which is more conjugated. Then look at the Gaussian images, determine from that which is more conjugated, and then determine whether or not the two agree. Gaussian is a program for determining structures or calculating structures and electronic properties. This is cyclopentadiene-one. You can see this is rendered as a three-dimensional molecule which we can rotate in space. We can also add things to it. And so this is the builder. We can stick benzene rings on it. All right, so the thing to notice here is that we have overlapping hydrogens. So this can't happen. You can't have two atoms occupying the same space at the same time. This would lead to what's called steric strain. You learned about sterics in like nucleophilic substitution reactions, where crowding can prevent a nucleophile from getting in. So tertiary carbons don't tend to react with SN2. They tend to go SN1 for that reason. So this is an issue. And this is important because it means that those phenyl rings cannot all be coplanar with that central ring in the cyclopentadiene. So if we rotate this, think in terms of orbitals. To get conjugation, you have to have orbitals that are coplanar or parallel with one another. And so think in terms of a p orbital. I'm going to pick this carbon here. A p orbital, you've got two lobes up and down. And to get a double bond, of course, like here, you've got these two p orbitals. They're overlapping, and so you get your double bond. But you can also get conjugation, for example, between these two carbons. This one here, which is the ipso carbon on the phenyl ring, and this one here, which is part of the diene. When those are parallel with each other, you get some overlap and you get conjugation, and you get something, it's not really a double bond, but something between a single bond and a double bond, but it does lower energy. So electronically, this is favored. But because of the sterics, this is an issue, and we're going to have to break some of that conjugation and or rotate some of those bonds. If you've watched Dr. Donahue's video, you can see how we're doing that here. And at this point, we no longer have the steric strain or the overlap between the hydrogens of that one phenyl ring that we've rotated. We can relieve the strain here by rotating this bond as well. You can see we've now relieved the strain on both of those. The question is this really the structure? Do we have to rotate this as well? We do have still some potential that there is interference or repulsion between the electrons of this hydrogen and the p orbitals, that pi cloud that's around this phenyl ring. And so this is something that's a little difficult for us to look at and decide what is the optimal geometry. And this is where Gaussian comes in. It will do the calculations for us. We can tell it to set up the calculations. There are different types of calculation. We're going to have it optimize our geometry. Hartree-Fock methods are complete quantum mechanics. There are also density functional methods. We're going to go to something called semi-empirical. Empirical means it's based on experimental evidence or experimental data. We're not going to want to use entirely experimental. We're going to kludge that together, or the program mixes empirical with quantum mechanics to make the calculations faster. So we can do calculations in a few minutes instead of many hours, or even with a molecule this size, a few days. At this point, the calculations will start, and it will give a geometry where it will balance the energy favorability of having everything coplanar with the stresses that you come from the electron repulsions from the different atoms. Remember, valence shell electron pair repulsion from general chemistry. And this program does use quantum mechanics, but again, it accelerates the calculations a bit by supplementing that with experimental data as well. So calculations are completed. It will open a new window with the new structure. We'll rotate that around, and we will close this one, but I will point out these two we had as coplanar and these two as perpendicular. All right, so we've got this molecule where it shows the two phenyl rings down here as being nearly perpendicular, and these two not quite, but close to coplanar. Question, of course, is it coplanar enough that we get conjugation? We can see there's some twisting, and so our p orbitals won't be perfectly lined up. But again, this is something we don't have to make a judgment call on. The program can calculate molecular orbitals, and we can tell it we want to calculate the energy of the highest occupied molecular orbital, also called the HOMO. And now that it's done the calculation, we can have it show the results in the main window. So we've got our orbital, and we will tell it go ahead and show the surface. And this is the molecule with the orbitals. Now, these red and green lobes are in fact p orbitals. So we have here a carbon atom in the center. We have this orbital here, which I'm outlining in white, and another one down below. And if you think about it, this is a p orbital. We have that center atom, and then above and below we have two lobes. This is a p orbital. So what the red and green are showing are p orbitals. The difference in color has something to do with the sign of the wave function, which is not relevant here. When you talk about pericyclic reactions in lecture, you may see this. It does become important when you talk about stereochemistry of various pericyclic reactions, but here they're simply the two lobes of a p orbital. And so what we are seeing is the p orbitals of the molecule, and then since we have these colored p orbitals across these three rings, the two phenyl rings plus the cyclopentadiene, that is telling us that those are all conjugated. You'll notice there is no real coloring on the two perpendicular phenyl rings. This is because those two are not conjugated. And so by drawing this molecule out and then running these calculations, we can see the extent of conjugation on the cyclopentadiene. There are pictures of both of this and the tetraphenyl naphthalene on As You Learn. You can download those. You will put them in your report and compare the extent of the conjugation. In this case, we have 6 carbons on each of the phenyl rings that are conjugated, plus the 4 in the cyclopentadiene ring, for a total then of 16 carbons that are involved in the conjugation. Do the same thing with tetraphenyl naphthalene. Count up the number of carbons that are covered with these orbitals, how many are involved in conjugation, and that tells you the relative degree of conjugation in tetraphenyl cyclopentadienone versus tetraphenyl naphthalene. And this is what you will compare with the UV visible spectrum.